All right, number 90. First thing we should do, draw a picture. Does the picture actually help us solve? Well, it gives us a visual of what's going on. Okay. So there are my two basically parallel lines. I need to choose one of these points. I'm going to choose that point as my first point. So that's going to be 0, 1. And I will need a second point. The second point has to be on the other line, and it has to be on a line that's perpendicular to both of our parallel lines. So we need an equation for that perpendicular line. So that's going to be y equals negative 1/3, because negative 1/3 is a perpendicular slope to 3, times x, and plus we need a slope, y-intercept, which we have right here. It's going through the intercept of 1, so same intercept. That's the equation of our perpendicular line. We need to know where it crosses the second parallel line. This is the second parallel line. I'm going to write it right below. So I need to now solve for this system of equations. If you have the opportunity to use technology, you just write these two equations in your calculators, and then there's an intersect function in your calculator, and it will give you the location of that second point. For our purposes, I'll solve it by hand. I'm going to use elimination, so I'm going to subtract these two equations. So I get y minus y is 0. Negative 1/3 minus 3 is negative 3 1/3. I'm going to write that as an improper fraction. That would be, thank you, negative 10/3. Very good. X, 1 minus a negative 3. That's the same as adding, so it's going to be 4. And now I have an equation where I can solve for x. I'm going to move the 4 over. Becomes negative 4. Equals negative 10/3 x, and then I'm going to multiply both sides by the reciprocal of negative 10/3 to get x by itself. So negative 3 over 10. So I get x by itself, because this becomes negative 30 over 30, which is just 1. Over here I get positive 12 over 10. So x is 1.2. There's your x value. Pretty fast, I know. Again, that's just algebra to figure out where that second x-coordinate is. So now we're going to plug that in to either one of these equations to find our y value at that point. It does not matter which equation we use. I'll use the second one because it looks a little bit more friendly, right? Less fractions involved. Not that I'm afraid of fractions, but some of us might be. Should I use? I'll use 1.2. That's fine. I can use either number. It doesn't matter. So we get y equals 3 times 1.2, that's 3.6 minus 3, so y is equal to 0.6. Okay. So my coordinate for the second point is 1.2 comma 0.6. We use that and the distance formula. Okay, can we see that okay? So distance formula, subtract your x values. So it's going to be 1.2 minus 0 squared plus, not far enough out, 0.6 minus 1 squared. And that's approximately 1.21. 6, 1.26. The other one was 1.21. And no, I did not do that in my head and take the square root of that in my head. I wish I were that smart, but no. I just know that having done this problem 3 times already yesterday, I remember the answer. Okay? You're like, well, how would we get it? Well, at this point, it would be a calculator problem. I would not expect you to do this by hand at this point. Okay, taking the square root of 1.6, no, that's ridiculous to ask that of you. Okay.
You said for sure they're not going to have that on the calculator test?
Didn't say anything like that. No, ma'am. I wouldn't say anything one way or the other, because that would be me giving you information. Yeah, I'd be cheating. I would not be ethical. All right. You are welcome. Anything else from page 5? We good? All right. Now, I know I flew through that. Are there any questions about the method itself? Yes, ma'am.
Can we go over 66?
We can. Before I jump there, are there any last questions about number 90, guys? Okay, so just for your information, to remind you what we did, 3 things. And beyond drawing the picture, I needed to have I needed 2 points that lay on a line that is perpendicular to our 2 parallel lines. That's what we needed so we could find the distance and use the distance formula. So first, we chose a point. Second, we found the perpendicular line that passed through it. Third, we found where that perpendicular line intersected our second parallel line. Got that coordinate, and then we used the distance formula, and we got our answer. So it's like a 3 to 4 step process. They're big steps, but there's only 3 or 4 steps here. Okay. All right, number 66 is being requested. Let's have a look. It says here, find the translation that moves pentagon 1 to pentagon 2. I'm asking for a vector. So what's the vector that takes pentagon 1 up to pentagon 2? Am I moving it all in the x direction? No. So 0 there. What's the y value? 4 up. Okay, so positive 4. This would be the translation vector that takes you from pentagon 1 to pentagon 2. Now, just to make sure you're aware, there's a second way to write this type of notation. This is called vector form of translation. The other way we could write it looks like this: x comma y, and then an arrow, and then x comma y plus 4. Can you see how these two things are related?
Yes.
This says here's where I'm starting off, here's where I'm going to end up. This says I'm going to end up 4 units above where I started off, basically. So basically they've taken this vector and they've added it. That's what they've done. These mean the same thing to us, though. Okay, so we should be able to go between them and go, oh, okay, yeah, I know what happened there. Is that sufficient, or do you need to see the others as well? Because that was just from 1 to 2. They also wanted you to do 2 to 3 and 3 to 4.
Can we go just with 2 to 3?
Sure. So I'm going to choose just one of the points on this pentagon. Since it's a translation, this thing's not going to be twisted or turned at all. It's going to be keeping the same orientation. So that corner corresponds to this corner. Okay. How far have I moved that corner in the x direction? Hearing 8. Did anybody get 8? 7? Okay. 1, 2, 3, 4, 5, 6, 7, 8.
Oh, no, never mind.
It's 8? Okay, so 8 over how much up? 1. There's your vector. Translations are all about sliding something along. So this says slide it 8 units over and 1 unit up. Okay? Easy enough? Excellent questions. All right, turn the page. Anything from page 6? Okay, this is, again, answering any questions from the homework sections. Okay, do you have anything on page 6 we need to talk about, or we need to move on? Speak now. It's okay if you do. That's why we're doing this. 98? Okay. They want us to find the geometric mean between these two pair of numbers. Here is the pattern. It says you want to find the geometric mean between two numbers a and b. You use this proportion. A is to x as x is to b. A and b would be called our extremes, and the x values would be called our means of these extremes. So to solve this type of problem, you would cross multiply. You would get x squared equals a times b, and then you take the square root. So same thing here. We will do 11 is to x as x is to 14, and cross multiply. We get x squared equals 11 times 14. So what, 154? So take the square root of both sides, and so you get x is equal to the square root of 154. I guess the question that you had was whether to choose C or D. Am I right? Yes. And so this is ambiguous. Since it doesn't specify, both numbers technically have can be right in their own right. Which one would be the most correct? C would, because this had to be rounded off, right? So this is the more correct of the two answers. And of course, guys, when it comes to these types of problems, the default for me is always choose the thing that has the most exact answer. Okay, go with the most exact. It's easy to convert this over to 12.5 something. It's really hard to go from the decimal back to the most exact form, because you had to round off at some point in order to write it as a decimal. So be aware of that. Okay. Exact answers are always better. Okay. Anything else from page 6? Okay, page 7, turn the page. That's okay if there's no questions, that's great. If there are, that's great too. Anything from page 7? Say again, 110. Okay. There is, the first sentence is the important thing. It's one of the things people skip over. It says here ZC, segment ZC is an altitude. Folks, tell me what you know about altitudes. Yes, and that's the key. It makes a 90-degree angle with the side that it hits. So folks, if you would please, make a 90-degree angle. When you do so, what type of triangle do we now have? So that means these two other angles are complementary. They add up to 90 degrees because you already have 90 degrees taken care of. So these two have to add up to 90. So just add these two angles, set it equal to 90. Okay, that's it. That's how you solve this problem. Okay, do you need me to actually solve it? Your call. Is the jury out? Yes? No? Okay, that's fine. That's fine either way. So it says here CYW. CYW, that's this angle here, is 7x plus 21. And it says WZC. WZC, this other angle, I mark with a double arc, is 16x. I'm going to add those together. If I do so, I get 23x plus 21 equals 90 degrees. Which means that 23x is equal to 69 degrees. So x, if I divide both sides by 23, is 3. That's what x equals. That, of course, is not my answer. They want us to find WZC, which is this angle right here. So I'm going to have to do 16 times 3, which is 48 degrees.
Mr. Duncan?
Yep.
Isn't it 68 for instead of 69, 68?
It's 21, so when you subtract 1 off, you'll get 9. If it was 22, then if this was a 22, then it would be 68, yes. Okay. Fair question, thank you. All right, so the answer is C. All right, anything else, folks, on this page?
118.
118, okay. So this is a good problem. It says here that this swimming pool is equidistant from all three buildings. Oh, that doesn't help that you can't see it. There we are. All right, it says the swimming pool is equidistant from all three buildings. That means I could draw a circle and it would hit all three corners. It would pass through all three corners. This would be the radius of that circle, right? All three of these would be the radius. What point, what special point would that be called? The center. In center is when you have a circle that's inscribed in a triangle. And if that's the case, you would have something like this. That's an in center right there, where all the circle is inscribed inside the triangle. Here, the circle would pass through all 3 points. It's not an in center. What's the other one? Not centroid. That's for medians. The other one, what's the word when you're going around a circle? What's the word? So there's word circumcenter. Yes. Okay, and I think this one throws people off because they see that swimming pool. They're like, "Oh, it's a circle inside a triangle. It must be an in-center," and it's not. Okay, because it says the swimming pool is centered at the point that's equidistant from all 3 points. Okay, Circumcenters have loads of applications. If you're going to put a cell tower down someplace so that everybody has equal coverage between, like, say, maybe 2 or 3 cities, 3 major cities, then I would need to know where the Circumcenter is between those 3 cities. That would be the spot that gives everybody equal coverage, right? It reaches everybody at the same distance. Okay, same idea. It's also really good if you have to babysit and you have 3 kids that always are moving around. You want to be equidistant to all 3 of them in order to keep your eye on them, right? Right? So I kid you not, if you watch, you can do this. It's great. If you watch footage of trained babysitters, people who work with young children, if there's groups of them, you'll find them that they're always kind of in the midst of the kids. They're always kind of dead center. And that dead center, I kid you not, their mind has told them, stand here, it's the best spot. Right? Because after so long, they're like, I can reach everybody from right here. Okay, you will see them standing where the circumcenter would be mathematically. So it's something that happens in the real world. We see it when we do research, and that makes sense because it's the best spot, right? Because you can get to everything very quickly. Okay. All right. That being said, turn the page. I don't think there's anything else on this page. All right, page 8. Anything on page 8? The question that came up the most on page 8 was, I think, 129. Do we need to talk about it? Yes, no?
Yes.
Yes.
Okay. The secret to those problems on the right, is this thing that should have been moved. I thought I formatted this, obviously not correctly. It says here in the figure you have these two rays. They're opposite rays. That means you have a straight line. Okay, great. And angle 1 and 2 are congruent. So I should mark that in our picture. These two angles are congruent. That's going to be useful. And it says that KM, ray KM, is bisecting this angle in KL. So there's in KL. If KM is bisecting, that means these two angles being formed must be congruent to each other. So we got two pairs of congruent angles. All right, that's useful. Okay, so with that information, let's look at 129. It says if the measure of LKN is 6W minus 10, so LKN, that would be these two angles, basically, 6W minus 10. Okay, great. And the measure of JKP is 2W plus 5. Well, here's the thing. If JKP is 2W plus 5, what's angle 2 going to be? Same thing, right? Because they're congruent. So really, we just need to double this angle. This is 2W plus 5, double that quantity. And if we add it to this quantity, what should we end up with, guys? 180 degrees. It makes a full, it makes a straight line, doesn't it? Right? That would give us a full straight angle. So double it, you get 4W plus 10. I'm going to add to that the other angle. I love stacking when it comes to adding stuff up. It makes things so much easier. It gives you 10W, those go away, equals 180 degrees. So W is 18. There's our answer. Okay. That was whirlwind quick. Did I lose anyone? All right. Well, the trouble is, if I lost you, you're like, you can't hear me. I'm lost. Right? Turn the page. Right? That's like the wayward parent. Did I lose anybody? They're not there to say yes. Right? It's a silly question. Stupid question. Okay. So sorry, folks. Okay. We are now on to the new material. So I'm going to again do 25 problems with you. I will stop about halfway through, give you a break, because otherwise you just come like, okay, it's too much math, can't do it. Right? In fact, I'll say that for me. I'm like, okay, that's too much math. I can't do this. So we will take a couple minute break about halfway through. Are you ready to plow ahead?
Yeah.
All right. As we do so, here's something you need to keep in mind. Are you listening? Okay. You're right there. I see you. Okay, we have found you. Here's the thing to keep in mind, guys. Most of the problems we're going to do today involve similar triangles. What do we know about similar triangles? Like the big thing with similar triangles.
Similar angles.
The angles are congruent. What else? The sides are what? Okay, proportional, which means we can make a ratio of their sides and set them equal to each other. That, I kid you not, is going to be like the theme through the next 4 to 8 pages. You're like, oh, it's the same thing again. Oh, it's the same thing again.
Wait, can you repeat that you said?
Sure.
Congruent angles?
So similar triangles have congruent angles. We know that, right, by angle similarity. And similar triangles are proportional. Their side lengths are proportional to each other. You can multiply one triangle by a scale factor. It gets you to a bigger triangle or a smaller triangle.
They're similar.
Because they're similar, yeah. And that's what leads us into geometric mean. That's how we get geometric mean, is similar triangles. That's how we get trig ratios, sine, cosine, and tangent. We get those because of similar triangles, because they're similar to each other. They have these proportions. They're the same. Okay, if you would please, let's do number 130 together. 134, and I'll do 138. Should be a good spread for that page. All right, this first problem. Notice we have a triangle, and inside the triangle we have a line that's parallel to one of its sides. Do you see that? Those little arrows, very hard to see. This is called, the theorem that we're going to use for this is called the triangle proportionality theorem. I'm going to write it up here. That way you can reference it later if you need to as you're studying. Triangle proportionality theorem states, hey, if you got a triangle and you have a side length in it that's parallel to one of its sides, you have a line going through that's parallel, it creates similar triangles. Okay. The reason being is because if these lines are parallel, then the corresponding angles are going to match up, right? So you got congruent corresponding angles. So you have similar triangles, which means the side lengths are, magic word, proportional. Proportional. Parallel lines in a triangle like this give you proportional sides. And the triangle proportionality theorem goes a step beyond that. So instead of just saying that the triangles have proportional sides, it actually makes the triangle have segments that are proportional to each other as well. So we could say then that x plus 2 over x plus 5, right, if we add those together, is equal to 4 over 6. That's just straight up triangle similarity, right? Proportions between two similar triangles. This theorem says we don't have to compare the triangles to each other because the segments that are being created, they themselves are proportional. So we can instead say x plus 2 over 3 is the same as 4 over 2. Okay, because that whole thing's 6, so that's 4, it must be 2. So this is a proportion you could use. X plus 2 over 3 equals 4 over 2. That's the triangle proportionality theorem. Incredibly useful. Now, could you use similar triangles here? Sure. That's absolutely fine, right? That's like using the Pythagorean theorem when you could use a trig ratio. Trig ratio works all the time, Pythagorean theorem. It's nice, but it's a little more basic, right? It's a little more primitive. Okay, cross multiply, and we can solve this. So we're going to get 2x plus 4 equals 12. And I'll do some quick math there. X equals 4. 2. X equals 2. You saw nothing. Oh, it's being recorded. Dang it. Caught. Now, that's not my answer, though. Got to substitute that back in to get CF. So this should be 2 plus 2 is 4. So the entire thing. I feel like that number was right. It was 4. Who ruined this? What happened? I can't even erase it. What the sabotage is going on today? Oh, that's it. Mr. Duncan's day is over. Going home. Everything's ruined. Go home. Let's all take a nap. Can't do this. Okay. That's all it took to break him. One broken ribbon. Okay, so x really is 4, which means up here that would be 4 plus 2, which is 6. Haha, I saved that at least. Okay, which means the entire thing is 9 because it's 6 plus 3. Whew. And this, ladies and gentlemen, is why we use pencil. Because it covers up our mistakes, whereas red makes it glaringly obvious. Yeah, I know, but here is my cover-up, and somebody ruined my cover-up. Yeah, that's it. All right, next problem. Moving on from the abomination. 134. All right, here it says the instructions at the bottom of that page, which should have again moved to the top. I don't know what is going on with my formatting. It says determine whether each pair of triangles is similar, and then justify your answer. Okay, so we're looking at these two triangles. Folks, to remind you, similarity, triangle similarity, there's only 3 ways to test for similarity. You can test by angle. If you got 2 angles, you're good to go. The 2 triangles are similar. If you can show the 2 angles are congruent, you're good to go. If you can show all 3 sides are proportional, right, you do a ratio of all the sides, you get the same number each time, then it's similar by side, side, side. And the third way, and the way that people usually screw up the most, is side, angle, side. That's where you show that 2 sides are proportional and the included angle in between those sides. Right? So if you can show that included angle is congruent and the sides are proportional, then you can use side, angle, side similarity. If you don't have any of those, we do not have enough information to show that triangles are similar. Okay. All right, so let's look here. We only have one side, so that's not going to give us side, angle, side, or side, side, side. So that's leaving us with angle, angle. Do we have enough to show angle, angle similarity? And if so, what angles are congruent? Which angles do we have, if any? We have vertical angles. Very good. That's one angle. Do we have any other angles? Something about these lines being parallel. What does that give us? Not bad. Corresponding is a type of angle you do get with parallel lines, but there's no corresponding angles here as such. What else? Alternate interior. Yeah, so angle F is going to be congruent to angle J. Those are alternate interior angles. They make the Z. You notice that? the Z shape. Okay, those are alternate interior angles. And actually, that's all we need is two angles, right? Angle similarity. But we actually get all three angles. Why do we get all three angles? We also get angle G and K because they're also alternate interior angles, folks. That's the thing you just used. I'm a little concerned. Getting some blank looks like alternate interior angles. Did you just say that? Yes, yes. Okay. We also get the third angle to be congruent by a certain theorem. What's it called? There it is. Okay. Two angles are congruent in a triangle forces the third one to be congruent. Yes. So we can say, yes, they are. So we need to make a statement here. Triangle FGH is similar to triangle, and now we have to be very careful. What's the name of this other triangle going to be? It has to correspond correctly. J, K, H. All right. So the order is really crucial there because you're trying to tell them how these triangles correspond to each other. It tells you which sides are proportional. And we say that's true by angle, similarity. That's the abbreviation for similar, right? But that's the symbol that means similar. So angle, similarity. Okay. I think we're ready for 138. Jump down there, please. All right, let's see if we have enough. What things do we have here? We're testing for similarity still, guys.
The congruent top part.
Top part? So we have a pair of congruent angles. Okay. So we have angle similarity. Okay, do we have any side proportions that are proportional? I think some of you have forgotten how to check to see if these sides are proportional. Is 4 over 10 the same as 8 over 20? Yes? So we do get a side and another side. Do we have enough to show these triangles are similar?
Yes.
By what? Angle, side. Is that a similarity?
No.
I'll underline it so that way I can really drive it home for you. Do we have a similarity? No, that dog won't hunt. No, absolutely not. That's not side angle side, guys. Just because you got two sides and an angle does not mean it's going to work. It has to be in the right order. It has to be two sides and the angle in between them. Yep, SAS, not ASS. Okay? And yes, I wrote that on the paper. And yes, it's being recorded. And yes, I'm going to put it on YouTube. And all of you laughing immaturely, it's been recorded. Okay. So, the answer is no, there is not enough information. Technically, these triangles could be similar, but we do not have enough information to verify that. It's not enough evidence, okay? Page turn. I knew that would wake you up. A little bit of sass in the morning. Okay, let's do number 143, 147, and 150 together.
Was it 150 or on the benchmark already?
It was.
Was it? Oh, well, good. You're going to get a review of it then. Or rather a review. That's the right word. Not a preview, but a review.
150.
So let's see. 143, it says, a carpenter has constructed a chair like the one shown below. Very nice. Describe the type of lines formed by the front edge of the seat. Okay, there's the front edge of the seat right there. And a back leg. Let's look at this back leg right there. So there's a back leg. So those are two lines. This is 3D space now. We're not dealing with 2 dimensions. We're dealing with 3-dimensional space. They're asking us, what would you call those two lines in reference to each other? They're obviously not parallel. In order to be perpendicular, they have to intersect. It's a word, 4-letter word. Oh, I better not tell you that. You probably threw. Skew. Somebody said it. Well done. Skew lines. I shouldn't say 4-letter word because people start guessing the wrong 4-letter words. Oh, goodness. So is this incredibly useful? Not really. This is like identify vocabulary, right? Who cares? It's a skew line. Whoop-de-doo. To go askew? To go askew means like to go off a path that's like completely different and random than the path you were on. That looks pretty much what's going on here, right? Hey guys, let's talk about tacos. I want to talk about space. What? Why? Right? It's going askew. Okay. 147. Yes, taco conversations are always appropriate. Here we go. 147. It says here, Shannon wants to make a scale drawing of her car on a 5-inch by 7-inch index card, as you do. So let's draw a 5 by 7-inch card. So 5-inch by 7-inch. Okay. It says here her car is 12 feet long. Okay. Her car is 12 feet long. Hey, drawing a picture is important, right? I hope your car picture is accurate. Obviously, that's the most important thing on the test. Okay, now, and the length of this car, this 12 feet. So it's a very large car. Well, 12 feet is not too bad. Truck? Yeah, 12 feet is not so bad. It says here she decided to use a scale of 1 inch to every 0.5 feet. Let's convert that up. So 1 inch is half a foot, so that would mean 2 inches is how much? I've doubled, so if I go from 1 inch is 1 inch to every half foot, doubling that would be 2 inches to every what? 1 foot, yeah. So now we're dealing with whole numbers basically. That's fine. So this gives me a conversion rate. Now here's what I know. Her car is 12 feet long. So if she uses this particular scale, how big is her scale model drawing going to be of her car? Very good. It's going to be 24 inches. Yeah. What's the problem with that? What's the problem with it being 24 inches? Yeah, what's the problem with that, though?
Isn't that the index card? So
How big is the index card?
it's 5 by 7.
5 by 7. Is it going to fit?
No.
No. Which is basically, this is what it would look like. This is how much of the car she'd actually be able to draw. The rest of it would be over here somewhere, right? So the answer here is no. Scale model would be 24 inches, not 7 inches. Okay, so that's a problem. All right, you get the picture down, right? Okay, did you give it good wheels, high profile? Good rims? Good rims?
Rims are amazing.
Very important, your rims are amazing. And the sound system, wow, okay. 150, please. Okay, it tells you here pattern blocks can be arranged to fit in a circular pattern without leaving spaces. That's called, guys, there's a word for that, it's tessellating. To tessellate means to cover a plane and there's no spaces or gaps. Right, so you've completely covered a plane. Which you can see that's happened here in the shape. So it says here, remember that the measurement around a full circle is 360. Okay, great, so that's 360 degrees. It says here, find the degree measure of 1/3 of that angle. Well, let's figure out what that angle is first. How are we going to find the measure of angle 1? What we got to do?
Like, split the, you do 360 divided by 8.
Cynthia says 360 divided by 8. What do you guys think? That seems legit, right? Because those should be, assuming these are all congruent, of course. Yeah, that is legit. Too legit to quit, in fact. Now, is my answer 45 degrees?
No.
Okay, why not? Because.
You have to
Good
put
answer.
1/3.
Because it says 1/3. Very good. So 145 divided by a third is, 3 is 15 degrees. Nailed it. That question was on the benchmark? I don't remember that.
It was a fan.
Oh, it was a fan. Oh, okay, but yeah, and then you had to cut that 360 up into what, 5 parts or something? Yeah, and I think people made the mistake on the. I remember that problem. People were putting the wrong number down because they were going like 2 turns instead of just 1 rotation. They were doing like 2 rotations. So yeah, I remember that problem. It made me cry a little inside. I'm like, why are they getting this wrong? I know I taught them this. Okay, let's see here. I'll do 162. and 163, and 165. Okay. All right, it says here a tree is 44 meters high, casts a shadow 60 meters long, okay, like the picture shows. Write an inequality relating x and y, and then solve for x in terms of y. Well, I look at this, can you see that this angle out here is an exterior angle? So these two angles, therefore, would have to add up to equal that angle by the exterior angle theorem, which means, what's the relationship between this angle and this angle out here? If it takes these two to add up to equal this, what can we say about these two angles?
You subtract that one is greater than that.
Yeah, you can say that this interior angle's got to be smaller, right, than this guy. Makes sense, because if you have to add something to make it equal, by itself it must be smaller, right? That's your inequality. That's it. So you would say that 2x is less than y divided by 2 plus 4. So we did the first part. We've written an inequality. We got that taken care of. It says now they want us to get x by itself. What should we do?
Divide.
Sure. We can divide by 2. So if we do so, we're going to get x is less than. Now, this is the part where people kind of freak out. They're like, what do I do? Do I divide like the whole thing, part of it, only one of them? Let me show you how to make sense of this. I'm going to do the same problem over here, and you will be able to see exactly what you should do. What's the same thing mathematically as dividing by 2? Instead of dividing by 2, what else could we have done? Multiply by what? Yeah, multiply both sides by 1/2. That'll get rid of it, right? Multiply by the reciprocal of 2, that'll get rid of it. So do that instead. Yeah, so multiply by 1/2, because multiplying by 1/2 is the exact same thing, folks, as dividing by 2. Mathematically equivalent. Okay, so that gives us x is less than, and now we're just going to distribute the half to everything. What's a half times y halves? Why, it's y fourths. And a half times 4? 2. So same thing up here. Ultimately, I'm dividing each of these terms by that 2. So y divided by 2 is y divided by 4, and 4 divided by 2 is 2. So either way, you get the same answer. I'll be honest, when I first had to do division like this, when I was, in middle school and then high school, it bothered me because I'm like, do I divide part of it or all of it? I couldn't remember the rule. And then when I realized that this is the same thing, I'm like, oh, I get this. Like distribution, I get that. And so it helped me bridge that gap for me. Okay, maybe you'll do the same for you. Okay, that was easy enough. 163. Says we have similar triangles, so if they're similar, then their sides are proportional, right?
Yes.
Proportional sides. And folks, here's the other thing you have to be aware of. If the sides are proportional, then their special segments are also going to be that same proportion. So that means if we draw in the altitudes like they have here, the altitudes are going to have that same proportion. If we draw in the angle bisectors, they're going to have that same proportion. If we draw in the medians, they too will have the same proportion. So we can set up proportions between any of the parts of these triangles, except for their angles, of course. All right, so it says here AD is 12, FJ is 8, and AC is 16. And they want us to find FH. All right, so let's set up a proportion. I can say 16 is to 12 the same way that what? Close? X is to 8. You have to be in the same order. So notice I did side compared to altitude. So over here I should do side compared to altitude. Now folks, you can solve that. That's not a problem. You don't need my help solving that. I want you to know that that was one way to set up this proportion. Right? I did a ratio compared to a ratio. That's fine. You can also, instead of just using one triangle's ratios compared to another triangle's ratios, you can do corresponding parts. So I could say 16, I'm going to do that right here. 16 is to x, right? Side compared to side, the same way that what? Yes, as 12 compares to 8. So side compares to side the same way that altitude compares to altitude. Okay, both of these are going to give you the same answer. Doesn't matter. Cross multiply, you get, well, I'm just going to use slide rule. That's 16 times 8 over 12. And that should simplify, I believe, to 32 thirds. And if I cross multiply here, you're going to get the same thing. 12x equals 16 times 8. So x equals 16 times 8 divided by 12. That's the same thing we had up here. The same exact thing. Oh, let me scoot this up so you can see that. Same thing. So this will be 32 over 3. So there's my answer right there. Now notice D says 127 over 12. That, I believe, 16 times 8 is 127. No, it's not. 128? Okay, good. So, there we are. Folks, any questions here? Does it sit well? Not sitting well? Is it making sense? Is it not making sense? We're just... Okay. I'm getting worried. Are we getting close to a saturation point at this point? Yes. Okay. One more page of this, and then I'm going to give you a break so you can, kind of recollect and come back from all this math. Okay. So same thing we just did in 163. Same thing here. Instead of it being an altitude, it's just an angle bisector, but the rule is still going to be the same. You have similar triangles. AC is 13. FG is 8. FQ is 9. Okay, and they want us to find AP. All right, well, let's see here. It says here that AC is similar to FG. Okay, so those two compare to each other, and then the angle bisectors compare to each other. What's my proportion going to be? Okay, 13 over 8, you said?
Yeah.
Okay, equals x over 9? All right, excellent. Cross multiply and solve. So 13 times 9 over 8 equals x. I don't think that simplifies. That's 117 over 8. So, because they wanted AP, AP is the same as x. Yeah. Okay. All right, we good, folks? Questions? All right. Was I right about this whole section feels like it's about similar triangles?
Yeah.
Yeah. Turn the page. Oh, look, more similar triangles. Yay! Oh goodness, the cynicism. I love it. Oh, very, very nice. That's delicious. Very nice. Let's do 167. And let's see here. 168. Yeah, you've done problems like 166. You just did it. So 166 should be fine. 167. So here you don't have two triangles to compare that are similar. Instead, what you have is one triangle and an angle bisector going on. Here's a cool thing about an angle bisector. This is called the triangle angle bisector theorem. It doesn't get used a whole lot, but it is quite useful. It's one of those things that gets neglected, I think. It says if you have an angle bisector in a triangle, then it partitions your triangle into proportional parts. So we can now say that x minus 1 is to 3 as x plus 2 is to 4. So because it's an angle bisector, it's marked as such, these parts are going to be proportional to each other. It only works with angle bisectors, though. You don't. That same theorem does not work with the other special segments. Otherwise, they'd be included in the name. All right, cross multiply. Off we go. 4x minus 4, 3x plus 6, and now we do some quick math. Subtract the 3x over, you get 1x. Add the 4 over, you get right here. From here, I saw that I needed to combine like terms, so I subtracted 3x to this side. 4x minus 3x is 1x. I moved the 4 over to this side, so I added 4 to both sides. That goes away, so 6 plus 4 is 10. So that is what x equals, and that's all they wanted us to find. All right. 168. Similar triangles again. Lovely. It says here BD and QS are medians. If they're medians, that means that D is a midpoint and S is also a midpoint. Okay, it's nice to know. It says here AD is 6, which means the other side is 6. BD is 8. QS is 2x minus 1. And PS is x plus 4. Which means the other side is also x plus 4. Now, since these triangles, we're told they are similar to each other, that means we can set up a proportion. So I can say that 12, that's the 6 plus 6, 12 compares to 8 the same way that 2x plus 8 compares to 2x minus 1. All right. And guys, please let me know if you're concerned or not sure how I got those numbers, those expressions. You see the 12 is 6 plus 6? Mm-hmm. Can you see the 2x plus 8 comes from x plus 4 and x plus 4 combined together? Okay. Now, if we cross multiply and we solve this, we're going to get 12 times 2x minus 1. That's 24x minus 12 equals 8 times 2 is 16x. 8 times 8 is 64. Subtract the 16 to the other side. I believe that gives me 8x. Add the 12 to the right side, and that gives me 76. So x is equal to 9.5. And then we have to substitute it back in to get PS. So PS is 13.5. Ma'am.
Was it like I feel how you got an 8, but where does the x land? Like, is it because it says x plus 4, but where does the x go?
X plus 4 and x plus 4 becomes 2x plus 8. Yep. Just like I combined the 6's here to get 12. I said that side compares to this median the same way that this entire side compares to this median. Okay. Now, here's an interesting tidbit. We didn't actually have to use the entire length here. We could have done 6 compares to 8 the same way x plus 4 compares to 2x minus 1. We could have just done part of that side. So it'll still be, they're proportional, right? This is using these sides. If I divide both sides by 2, it's the same fraction, right? So I could just use 6 over 8 equals x plus 4 over 2x minus 1. You'll still get the same answer. I did it this way because it feels more consistent with what you've been doing so far. But ultimately, the answer is the same. All right, gang, questions here? All right, pretty solid? All right. That's a good stopping point. Let's take a break. Let's say about 2 to 3 minutes.